Hello everyone, this is Bsc second year real analysis class. So today we are going to discuss what is meant by Cauchy sequence. So write down the definition of Cauchy sequence. Cauchy is the name of a scientist which gives the criteria for the convergence of the sequence. So it is called as Cauchy sequence. A sequence Sn is called a Cauchy sequence. Is called a Cauchy sequence. Is called a Cauchy sequence or a fundamental sequence. Another name for this sequence is fundamental sequence or fundamental sequence or a fundamental sequence if for each epsilon greater than 0, if for each epsilon greater than 0, there exists a positive integer m. There exists a positive integer m. There exists a positive integer m such that Sn plus p minus Sn is less than epsilon for all m greater than or equal to m and p is greater than or equal to n. So this is the definition of Cauchy sequence or fundamental sequence. So Sn plus p means n plus pth term of the sequence and Sn means nth term of the sequence. If their mod is less than epsilon for all n greater than or equal to n and all p greater than or equal to 1, then we say that the given sequence is Cauchy sequence or Sn1 minus Sn2 is less than epsilon for all n1, n2 greater than or equal to n, then we say that the given sequence is Cauchy sequence. So these are the two definitions for the sequence to become a Cauchy sequence. So this is the definition of the Cauchy sequence. So note 1. A sequence of real number, a sequence of real number is convergent if and only if it is Cauchy. Now understand, every convergent sequence is Cauchy sequence. So this implies that every convergent sequence is Cauchy. And first, second, every Cauchy sequence is orthogonal. Every Cauchy sequence is orthogonal. So from this statement, we can write down these two things, which implies that a sequence of the real numbers is convergent if and only if it is Cauchy. So we can directly say that a sequence of the real number is convergent, then it is Cauchy, and if it is a Cauchy, then the sequence is convergent. Now, a sequence, note 2, note second, if a sequence cannot be Cauchy if we find at least one epsilon greater than 0 such that Sm plus P minus Sm is not less than epsilon for all n greater than or equal to m and for all p greater than or equal to 1, then we say that the sequence is not Cauchy. If we find at least one epsilon greater than 0 which does not satisfy the condition of the Cauchy sequence, then we say that the sequence is not a Cauchy. If it is not Cauchy, then it is not convergent, because there is a if and only if statement. If the sequence is convergent, then it is Cauchy. Now example depends on this theorem. Show that the sequence given sequence is Sn. Show that the sequence Sn where Sn is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by n is not Cauchy. If it is not Cauchy, then it is not convergent, because the only convergent sequence is Cauchy. Now the sequence Sn is 1 plus 1 by 2, 1 plus 1 by 2 plus 1 by 3 1 plus 1 by 2 plus plus 1 by n and so on. Now the given sequence is this. Now put n is equal to m and p is equal to m in the definition of Cauchy sequence and let epsilon is equal to 1 by 2. So we can choose any epsilon. Now from the definition, S to m minus Sm is what? So 1 plus 1 by 2 plus 1 by m plus 1 by m plus 1 plus 1 by 2m minus what is Sm? 1 plus 1 by 2 plus 1 by 3 plus 1 by m. So from this we can write it is 1 plus 1 by m plus 1 plus 1 by m plus 2 plus 1 by 2m. So we can say that it is greater than or equal to 1 by 2m plus 1 by 2m plus 1 by 2m, because every term 1 by m plus 1 is greater than 1 by 2m. This term is greater than 1 by 2m and this term is greater than or equal to 1 by 2m. So this addition of 1 by 2m is m times. So which is greater than m by 2m. So which is greater than or equal to 1 by 2, which is nothing but epsilon, and this is false. So it does not satisfy S to m minus Sm is less than epsilon. It does not satisfy this. Therefore, the given sequence Sm is not Cauchy sequence. Hence the proof of this example. Now I am going to discuss algebra of sequences, which means addition, subtraction, multiplication and division of the sequences. Now if An and Bn are the two given sequences, An and Bn are the two given sequences, then addition is defined as An plus Bn. Subtraction is defined as An minus Bn. Division is defined as An by Bn, where Bn is not equal to 0, and multiplication is defined as An into Bn. So this is the algebra of sequences. That means addition of two sequences, multiplication of two sequences, division of two sequences and subtraction of two sequences. Now we are going to discuss one important theorem, theorem 16. Theorem 16. If An and Bn are two sequences such that limit of An is equal to A. That means the sequence is convergent and it is converges to A, and limit of Bn is equal to B. This means the sequence Bn is converges to B. Then first, limit of An plus minus Bn is equal to limit of An plus minus limit of Bn, which is equal to A plus minus B. Second, limit of An into Bn is equal to limit of An into limit of Bn is equal to AB. And third part, that is division of the sequences, limit of An by Bn is equal to limit of An divided by limit of Bn, which is equal to A by B, where Bn is not equal to 0. Now I am going to prove first property. Given that limit of An is equal to A and limit of Bn is equal to B. And so if these sequences are converges to A and B, then there exists M1, M2 belongs to set of natural numbers such that An minus A is less than epsilon for all n greater than or equal to M1, and Bn minus B is less than epsilon for all n greater than or equal to M2. Let epsilon is equal to M is equal to maximum of M1, M, M2. Then if we choose maximum between M1 and M2, then we can say that An minus A is less than epsilon and Bn minus B is less than epsilon for all n greater than or equal to M. Now consider epsilon value. So choose epsilon to be epsilon by 2. Now consider An plus minus Bn minus of A plus B. So this can be written as an minus a plus minus bn minus b. Now this is what is less than or equal to an minus a plus minus bn minus b. Using the property that a plus b is less than or equal to mod a plus mod b. So this is what epsilon by 2 plus epsilon by 2 which is equal to epsilon. So we can say that this sequence an plus bn minus a plus b is less than epsilon for all and greater than or equal to half. This implies that limit of the sequence an plus bn is equal to a plus b. So limit of an plus bn is equal to a plus b, which is nothing but limit of an plus limit of bn. As the proof of the first property of this theorem. On second property, given that limit of an equal to a and limit of bn equal to b. That means the two sequences are convergent. Therefore, they are bounded. We know that every convergent sequence is bounded. So we can write an is less than or equal to small k and bn is less than or equal to capital K. Since they are bounded, these two sequences are bounded. Also they are convergent. Now consider an bn minus ab. It can be written as an bn minus an b, add and subtract an b minus ab. So from this we can write, if we take an common, an into bn minus b, plus take b common and bn minus b. So from this we can write, which is less than or equal to mod an mod bn minus b plus mod b into bn minus b. This is an minus a, minus a. This is an minus a, minus a. Now choose epsilon 1 to b. Now from this we can write it is less than or equal to mod a is less than or equal to k into mod bn minus b plus mod b as it is and an minus. Now choose epsilon 1 to be epsilon by 2 divided by small b and epsilon to be epsilon divided by 2 divided by mod b such that an minus a is less than epsilon by 2 divided by mod k and bn minus b is less than epsilon divided by 2 upon mod b. So from 1, put these values in equation 1. So from 1 we can write down that upon k plus, which is less than or equal to mod b upon epsilon by 2 divided by mod b. So this get cancelled. So which is equal to mod epsilon multiplied by epsilon multiplied by epsilon for all n greater than or equal to m. So from we got AMBM minus AB is less than epsilon for all n greater than or equal to m. Hence the sequence AMBM is converted to AB. That is limit of the sequence AMBM is equal to AB. It is equal to limit of AN into limit of B. Hence the proof. Hence the second property. Now third property is for homework, so it complete it and WhatsApp me by taking photograph of this proof of part 3 of division of the sequences. So today's lecture I am going to stop over here. Thank you.